At this very moment, satellites are drifting silently above your head, not just one or two, but thousands of them. Most are harmless, providing the internet, tracking weather patterns, or helping planes navigate across the ocean. But a few exist for more ominous purposes: to observe, to monitor, and in some cases, to control. From their orbit, they can read the labels on a bottle. They can track an individual moving through a forest. And some of them may never appear on any public satellite registry. For decades, military and intelligence satellites have been watching the world, shaping conflicts and altering geopolitics, while raising unsettling questions about privacy, autonomy, and power. Their full capabilities remain largely unknown. Let us look at a side of aerospace technology people rarely think about: the hidden evolution from simple balloons to secret orbital reconnaissance platforms. It is a long story, so let us begin our journey in the realm of dreams. Before we start, do not forget to like and share. In the mid-19th century, long before man-made satellites circled the Earth, humans were already searching for ways to see further from unprecedented heights. Observing from above was not a new idea, but the means to achieve it were limited. Simple experiments with hot air balloons eventually grew into one of the most secretive and advanced fields of technology: reconnaissance from space. During the American Civil War in the 1860s, both the Union and the Confederacy used balloons to observe enemy troop movements. These early platforms were nothing more than canvas balloons filled with gas and tethered to the ground. The observers, holding telescopes or sketchbooks, were primitive and basic, yet they provided the military with a completely new perspective. They could now look down from hundreds of feet in the air, a vantage point that had never existed before. This idea caught on quickly, and over the next few decades, military planners and inventors pushed for constant improvements. Some tried mounting cameras to these platforms, but the results were mixed. Early photographic equipment was large and fragile, and movement from wind and rain made clear imaging difficult. Nevertheless, the potential was clear: if you could send a camera high enough, you could map enemy positions, monitor infrastructure, and track movements without ever setting foot on the ground. At the turn of the 20th century, another strange but clever idea emerged: using pigeons. A German pharmacist named Julius Neubronner invented a lightweight camera small enough to be strapped to a pigeon's chest. As the bird flew its usual route, the camera used a simple timer to take photos automatically as it glided over the ground. Today, it sounds almost charming, but before the age of drones or satellites, this was an early form of aerial intelligence gathering. These photos were grainy and often tilted or blurred, but they represented a genuine breakthrough: photography from a great height, quiet, and without risking a human life. The First World War pushed balloon-based surveillance even further, but it also marked the beginning of another leap: airplane pilots carrying cameras over enemy lines. Reconnaissance changed from a game of chance into a specific mission. Planes could fly farther and faster, and new cameras were being developed specifically for high-altitude work. By the Second World War, aerial photography had become a science. Specialized reconnaissance planes flew dangerous missions deep into enemy territory, capturing detailed images of defenses, convoys, and industrial targets. But even planes had limits. Weather, anti-aircraft fire, and human error made every mission a gamble. There was a constant need to fly higher, faster, and more secretly. As rocket technology began to emerge in the 1940s and 50s, pioneers started to imagine something entirely different, putting observation platforms into space. The Cold War pushed this idea into reality. In 1957, the Soviet Union launched Sputnik, and the space age officially began. The United States quickly responded with its own satellites, and at the same time, secret projects to use space for spying were unfolding in the shadows. The first true success came from the Corona program, which was classified at the time and remained a secret for decades. Corona satellites were designed to orbit the Earth and photograph Soviet missile bases and military installations. These satellites carried film cameras and would drop small return capsules containing the film back to Earth. These capsules would fall by parachute and be intercepted in mid-air by specialized planes, a stunning combination of precision engineering and espionage. In the early 60s, the first Corona missions could only capture objects the size of large buildings, but as technology improved, the resolution became sharper. Engineers developed better lenses, more stable platforms, and more sensitive film. By the 70s, Corona satellites could capture objects only a few feet wide from hundreds of miles away. At the same time, optical technology was making a leap forward. Ground-based telescopes were modified for space, and cameras that once required physical film began to shift toward digital sensors. Satellites no longer needed to drop film capsules, they could send data directly back to the ground via encrypted radio links. This near real-time capability changed everything. Intelligence agencies no longer had to wait hours or weeks to see what the satellite had captured. The demand for higher resolution and greater secrecy continued to drive innovation. Some satellites were so advanced they used reflective mirror systems similar to astronomical telescopes. These mirrors had to be perfectly polished and positioned to focus on a target from hundreds of kilometers away. Even a tiny shift or temperature change could ruin the image. Despite the challenges, the rewards were massive. Sub-meter resolution images could identify a vehicle, a runway, or even the hatch on a submarine. All this precision and the ability to stare at a single building from space grew from those early steps with balloons and pigeons, driven by the urgency of the Cold War. The goal remained the same, to see what others did not want seen. And the methods evolved to a point that 19th century observers could never have imagined. Even today, the most powerful reconnaissance satellites remain classified, with details about their size, orbits, and capabilities closely guarded. But based on public data and expert analysis, some are believed to resolve details as small as 10 centimeters fine, enough to read markings on a runway or spot a camouflage tank under a tree canopy. These platforms fly silently above the Earth, following predictable paths and collecting multispectral images to feed data to analysts and decision makers. Modern commercial satellites now offer the public a taste of what was once top secret. Companies like Maxar and Planet Labs operate constellations that can produce clear, colored images of almost any location on Earth. Capabilities that once belonged only to military intelligence are now available to researchers, scientists, and the public. But their roots trace back to canvas balloons, fragile film, and bold guesses. The launch of the first true spy satellites was not met with grand announcements or live television countdowns. Instead, the missions were shrouded in layers of secrecy and official denials. In 1960, when the first successful images from high-altitude satellites returned to the ground, very few people knew what the Corona program even was. It was the American answer to a growing problem during the Cold War, the inability to see what the Soviet Union was building. Since the late 50s, U-2 spy planes had been flying over Soviet territory, but the risk was extremely high. In May 1960, Francis Gary Powers was shot down while flying over the Soviet Union, forcing officials to rely more on satellites. They needed a way to see without being seen. Corona satellites were built under the name Discoverer, and the public was told it was a space science program. NASA even helped maintain this illusion by releasing false mission goals and vague scientific statements. But the true purpose was entirely different. These satellites carried cameras, not experimental equipment. Their job was to photograph missile sites and air bases and bring that film back to Earth. The success of Corona eased Cold War tensions in unexpected ways. In an era of mutual distrust, the most dangerous part of the arms race was uncertainty. American leadership feared a missile gap, believing the Soviets were building far more missiles than they actually were. But Corona showed that this gap did not exist. The Soviet arsenal was smaller than feared, allowing analysts to track new developments more accurately and reducing the need for blind expansion. Corona ran until 1972 and was succeeded by a more powerful series called Hexagon. During its service, the name Hexagon was never made public. Internal documents referred to it as Keyhole 9. Hexagon was far more advanced than its predecessor, larger, heavier, and equipped with better cameras. Some models carried multiple film return capsules, allowing for longer missions. It used a complex mechanism of rotating lenses and mirrors to scan the ground in a wide sweep, covering vast areas while maintaining high resolution. Some versions could identify objects as small as 2 or 3 feet from an orbit of 100 miles. The precision of this era was breathtaking. Engineers had to manage the thermal changes in orbit and build cameras that could operate at thousands of miles per hour in a near vacuum. Every part had to be perfect because there was no way to repair them once launched. To maintain the secret, the government created cover stories, claiming these missions were for weather or scientific research. Even many people working in the industry did not know the true purpose of the missions. The facilities where these satellites were built operated under heavy security. In 2011, the Hexagon program was finally declassified, revealing its full scale. A satellite on display at the Smithsonian Museum allows people to see its massive complexity. Yet, even today, many details remain classified, including the exact resolution and the full capabilities of later models. Modern secret projects continue this legacy. High-resolution imaging, thermal sensors, and radar that can see through clouds and darkness are all part of the modern toolkit. Satellites today may no longer use film, but the pursuit of higher resolution and lower detectability never ends. Some systems use adaptive optics to sharpen images distorted by the atmosphere, while others fly in formation to share data in real time. Despite the changing technology, the core of the mission remains the same: to understand what is happening beyond the borders without intruding, watching silently from above, seeing without being seen. The Corona satellite on display at the Smithsonian looks like a relic from another era, with its polished metal casing and exposed camera system. Visitors walk past it, perhaps not realizing that this machine once changed the course of history. But what they see is only part of the story. The true innovations, the thermal control, the film handling, and the stabilization systems, remain hidden or obscured. The engineering that made it all possible is buried in archival blueprints and in the memories of those who worked in the shadows under silent contracts. The story of the Hexagon satellite is also only half told. Many of the exhibits are missing key components that were removed before public display. What remains is a reminder that even today, many of the technologies shaping the modern intelligence world are still kept behind locked doors. While the United States was quietly sending Corona and Hexagon into orbit, the Soviet Union was working just as hard to build its own eyes in the sky. The Soviets knew they had to monitor their rivals from space, but they faced a different set of challenges shaped by their own engineering doctrines and political pressures. Soviet space reconnaissance did not simply copy the Americans, it followed a path carved by Soviet institutional style. In the early days of the space race, they relied more on high-altitude planes and ground intelligence, but by the late 1960s, space-based imaging could no longer be ignored. American satellites were photographing Soviet missile sites, and Soviet leadership knew they had to catch up quickly. Two major programs came to represent the Soviet path: Cobalt and Yantar. The Cobalt satellites were first launched in the early 80s, though their design had been in development since the 70s. These satellites did not rely on digital transmission. Like early American systems, Cobalt used physical film, loading rolls of photographic material into the satellite and sending them back to Earth in special return capsules. Every few weeks, the satellite would eject a capsule, and Soviet recovery teams would track it down in vast forests or frozen landscapes under heavy security. The recovery process was like a major military operation, involving helicopters, radar units, and highly trained search teams. The imaging quality of Cobalt was quite high, enough to identify buildings, vehicles, and planes, allowing the military to track changes in construction at strategic bases. These insights were fed into the military intelligence system, influencing strategic adjustments across the Eastern Bloc. Soviet engineers constantly improved the system, eventually adding multiple return capsules and working to shorten the time between photography and analysis. The Yantar series was introduced as the next step to address the weaknesses of Cobalt. Launched from the late 70s and improved through the 90s, Yantar used a more modular design with better thermal control and a more stable platform. Its key advantage was longer time in orbit, with some missions lasting several months. Yantar was often equipped with advanced optical systems that could scan wide areas while focusing on specific targets. Some models used telephoto lenses and large mirrors to improve clarity, a direct adaptation of astronomical technology. In the early 2000s, a new series of satellites began to lift off from China, quietly entering orbit without grand announcements or detailed policy briefings. Publicly, they were described as being for scientific research, land mapping, or disaster monitoring. However, global defense analysts soon noticed a pattern. These systems shared a common name, Yaogan. Their launch sites were military facilities, and their orbits and launch rhythms suggested a different story. Yaogan is a broad and vague term meaning remote sensing, but experts suspected these systems were doing more than just looking at the weather. They noticed a mix of payloads, including synthetic aperture radar, optical cameras, and infrared sensors. China was quietly building a comprehensive space surveillance network. The Yaogan constellation grew rapidly. Some satellites entered sun-synchronous orbits to get high-resolution images under consistent lighting, while others were launched in groups of 3. These triple formations suggested a maritime surveillance role, helping to locate ships at sea through signal intelligence or radar reflections. Many of the early optical satellites likely carried high-powered telescopes capable of high-definition zoom. While the exact resolution remains a secret, analysts estimate it is better than 1 meter. Later versions added synthetic aperture radar, which, unlike optical cameras, can see through clouds and at night by measuring reflected electromagnetic waves. This allows for constant monitoring of large areas, ensuring that even if an aircraft carrier group moves under cloud cover, radar satellites can still find it and feed data to military planners. The triple satellite launches introduced another capability: signal intelligence. By flying in coordinated orbits, these satellites can triangulate radio signals, such as radar or military communications, to calculate their exact source. This allows China to locate the radar systems of ships anywhere in the Pacific. Unlike NASA or the American National Reconnaissance Office, which often publicize missions or release photos, China's space program operates under a deep veil of secrecy. There is no comparable transparency, launch announcements are minimal, and payloads are never shown to the public. Most of what we know about Yaogan comes from external analysts who track their orbits and estimate their imaging windows. By the mid-20s, over 100 satellites had been launched under the Yaogan name. Analysts believe this constellation directly supports military operations, including missile tests and naval deployments, and provides the real-time intelligence central to modern data-driven warfare. This shift toward digital imaging means data arrives faster and planning is more flexible. It also means China has built a secure network of ground stations to receive vast amounts of high-resolution imagery. Because of the high level of secrecy, international observers face a challenge. While a satellite's path is visible and predictable, what it carries and how it is used remains a mystery. This contrasts with the norms that evolved during the Cold War to avoid misunderstandings between superpowers. American and Russian reconnaissance. Satellites often leave a trail of intent through their public orbits or specific equipment. China's satellites, however, remain ambiguous, with identical announcements and subtle orbital adjustments that hide their true purpose. What is clear is that China has entered the top tier of space surveillance. The Yaogan constellation is a powerful tool for national security, using silent orbits and persistent eyes to usher in a new era of space power. Intelligence does not only come from what can be seen, increasingly, it comes from what can be heard. Even without a camera, a satellite can listen. Signal intelligence involves intercepting data through radio, radar, and microwave links. This field is often divided into subcategories, such as electronic intelligence, which focuses on non-communication signals like radar pulses or telemetry. Signal intelligence, often called SIGINT, focuses on the exchange of voice, text, and data between people or machines. Unlike imaging satellites that look down at the ground, SIGINT satellites act like giant antennas, specifically tuned to capture electromagnetic signals traveling through the atmosphere. They do not need clear skies or sunlight. They can collect data from vast distances, often covering targets that cameras simply cannot reach. While an imaging satellite might show you a radar antenna, a SIGINT satellite can tell you its operating frequency, how often it is turned on, how the signal is modulated, and its transmission power. Orbit is crucial in this field. One type of satellite stays in low Earth orbit, circling the globe quickly about once every 90 minutes, providing brief windows of coverage but returning frequently. These are perfect for tactical intelligence, snatching radar signals, communication bursts, or missile test telemetry as they pass overhead, before relaying the data to ground stations. For broader coverage, many platforms are placed in geostationary orbit, matching the Earth's rotation to hover fixed over a single region. A single satellite positioned over a hotspot like the Middle East can listen around the clock. These satellites are often massive, equipped with powerful antennas that unfurl into giant reflectors spanning dozens of meters, designed to capture faint whispers from thousands of kilometers away. Since the 70s, the United States has operated these geostationary listeners to monitor diplomatic communications, military radio, microwave links, and even shortwave broadcasts. Every signal is a puzzle, and analysts use wave shapes, strength, and timing to determine its source and meaning. Some systems specialize in tracking battlefield emitters like air defense or early warning radars. These radars turn on and off frequently and hop between frequencies. Passing satellites record these electronic signatures and match them against known databases, allowing the military to identify the type of equipment being used and whether new technology is being tested. Even today, despite encryption and frequency hopping making the work harder, these satellites are tasked with mapping enemy command structures and troop positions. When combined with imaging satellites, the insights become even more valuable. For example, if a camera sees new trucks and radar at a coastal base, the next question is whether that radar is operational. If SIGINT sensors pick up new, previously unused frequencies from that exact spot, analysts know the equipment is active and ready. Another silent workhorse of persistent surveillance is synthetic aperture radar, or SAR. While traditional optical satellites often return nothing but gray images over cloudy regions like Siberia, SAR can see through bad weather to identify airfields and missile sites. Unlike optical cameras that rely on light and contrast, SAR can detect if something has moved. It can see new tire tracks on a runway, tell if a field has been plowed, or track a moving truck. By comparing radar images taken hours or days apart, analysts can see exactly what has changed, even under heavy cloud cover. One of its most powerful tools is coherence change detection. By comparing the waveforms of two radar images taken from the same angle, SAR can reveal microscopic disturbances on the ground that a normal camera would miss. This has been used to identify underground tunnel networks in war zones by spotting tiny soil settlements or unusual moisture patterns. SAR is also vital for maritime tracking, as radar reflects strongly off metal hulls, allowing it to find dark ships that have turned off their transponders to engage in smuggling or illegal fishing. While a standard satellite camera might record only a handful of color bands, hyperspectral sensors span dozens or even hundreds of narrow bands, each only a few nanometers wide. By stacking these bands, the sensor generates a spectral fingerprint for every pixel in the image. Every material, whether it is paint, vegetation, concrete, or fuel, reflects light differently across the spectrum. Hyperspectral imaging originated in agriculture and geology to monitor crop health and soil composition. Intelligence agencies quickly realized its potential. It can be used to find hidden missile sites by identifying chemical residues from fuels, or to spot disturbed Earth long after an excavation has stopped. In one declassified case, hyperspectral data was used to find residues of highly corrosive oxidizers used in liquid missiles. Even though the launch site had been covered and the tanks removed, the chemical fingerprint remained in the soil and was detectable from orbit. It is also the ultimate anti-camouflage tool. Even if a vehicle is painted to match its surroundings or hidden under a tarp, its spectral reflection will still differ from the surrounding trees and grass. In some cases, these sensors can almost smell changes before they become visible. For instance, if traces of ammonium nitrate, a key ingredient in explosives, suddenly appear in a remote desert, hyperspectral sensors can flag the anomaly. At sea, it can distinguish between different types of oil or chemical spills, telling the difference between crude oil, diesel, or industrial waste, which is vital for tracking environmental violations or secret mid-ocean resupply missions. The amount of data generated is massive, requiring specialized software and vast computing power to match new data against libraries of known material fingerprints. While many of these high-end military systems remain classified, it is widely believed that they are used to monitor sensitive facilities for chemical clues carried by ventilation systems or drainage, providing a hidden layer of insight into what is happening deep underground. Here is the translation and adaptation of your text into a professional, podcast-ready narrative. I have smoothed out the transitions and used precise remote sensing terminology while maintaining a conversational flow suitable for audio. Despite the persistent interference caused by cloud cover, hyperspectral imaging possesses a remarkable ability to penetrate thin haze or localized clouds within specific infrared bands, allowing missions that would otherwise fail under visible light constraints to continue collecting vital data. Because these data sets are exceptionally rich in information, hyperspectral archives actually appreciate in value over time. Analysts can revisit legacy data using advanced spectral unmixing or sophisticated algorithms to uncover insights that were completely invisible at the time of capture. A stretch of highway or a patch of desert imaged a year ago might suddenly reveal traces of past activity when re-examined through the lens of new spectral fingerprint matching. This capability is central to systems like China's Tianhui and Jiaofen series, which are recognized for their hyperspectral payloads used to monitor overseas military installations, natural resource extraction, and environmental shifts tied to defense infrastructure. Similarly, Russia likely leverages its deep heritage in orbital remote sensing to apply hyperspectral surveillance for military ends. Although these sensors remain complex and expensive, requiring meticulous calibration and producing data volumes that often exceed real-time downlink capacities, many platforms have shifted toward robust ground-based batch processing. As computational power scales and satellite constellations grow, hyperspectral intelligence is becoming faster, more affordable, and increasingly automated. That concludes our technical deep dive for today. I wish you all a restful night and a wonderful day ahead. We will see you in the next episode.